Alright, we've done the first little bit on vectors where we spoke about unit vectors and how to write them and that lot. Now we're moving on to something else, which is position vectors, displacement vectors, how to actually add vectors. We've not spoken about that yet. And then on to how can you make them parallel. So I'll get this written on the board into some form of a title, then we'll get a whiz in. Right, I had to chop that title up a bit. Vectors, operations and displacement. We are going to do parallel vectors as well in this video, but first we're just going to look at the operations. So the operations that you can do in normal mathematics, just, you know, the four basic ones. We've got add, subtract, times and divide. So we're going to go through each one of those. We're going to start with the most obvious one, which is plus. Right, to get us started on this, we're going to look at two bog standard vectors. We've got vector A, let's say it goes along 3. Let's do this in another colour. Along 3, up 4. Then we've got another vector B, which goes, let's say this one goes down 4 and across 1. If we added these two vectors together, what we're actually doing is we're putting them on top of, well, not on top of each other, end to end. I shouldn't really itch my nose when I've got chalky hands. If you do vector A and then you do B afterwards, it's essentially just doing that and then putting B on the end of it. So what you're doing is you've gone along 3, up 4, then you've gone down 4, oh that's not to scale, and then across 1. Let's change this to say 5. And that one. Now it looks a bit more like it's to scale. So if you add these two vectors, what you get is, it looks like that, but then you just add each component of each vector. So the x adds the x and the y adds the y. So the end product is -2 and 5. Now this is how you add them. What if you were to subtract them? Well, interestingly enough, if you were to subtract them, it's the exact same thing, but you just minus them. What this would look like is if you did minus b, it's like b, but going in completely the opposite direction. So if that's b going down there, minus b takes you up there. So let's do a minus b. So you get 8, 2. Right, we've done plus, we've done minus. What's left over is times. Now, little confession, in A level you can't actually multiply vectors. It's possible, but that's really something for further maths. And that's where you do the scalar product or the vector product. Is that right? Yeah, dot product or cross product. That's what it's called. It's really useful in engineering and physics, like at university. But in A level, we're just gonna do timesing it by a scalar. So this is what it looks like. Right, this is kind of, I've written A as a generic vector, A1 and A2. What we've got is we're timesing it by some scalar, which is just a number, k. So it becomes k times this vector, which then it multiplies each component of the vector. So if we actually go back to our original one, so let's say k was 3, okay? So the end product is 9, 12. What that looks like is actually, it's a scalar, not the word, scale factor is the word I'm looking for. You've multiplied it by 3, which means you've done an enlargement of scale factor 3. Looking back at this original, what you've done is you've extended A by 3. So you've done another A and then another A. So all of that is 3A. You could do the same thing where you can make it smaller, where you do it a number which is between 0 and 1, squashing it. Or you could times it by a minus number, which is to say you're going to reverse it and do a scale factor. Now just as a little note, I'm going to say what vector multiplications you don't do at A level, just in case you see it in someone else's notes, like a friend's notes or on the internet. This is what you don't get to do. Right, so this one is called the cross product. This gives you a vector at the end. This is called the dot product. It gives you a scalar quantity at the end. Really, really useful, but not in A-level normal maths. So we've done times. Same as times, we can't really do divide. So yeah, we're just not going to do divide. And that is the operations. Okay, we're going to talk about position and displacement vectors now. We're going to start by talking about position vectors. Imagine we've got some coordinate system. This is the origin. If you're given a coordinate, we're going to call that coordinate A, capital A. It's here. Let's say it's 2, 3. Notice it's a coordinate, so I'm writing it as a normal coordinate, horizontal numbers. If you're at the origin and you go to A, that journey that you've gone from the origin to A is a position vector. It's taking you to the position of A. So we call that A. And the way that we write it with a little arrow along the top to say that we've gone on a journey from O, the origin, to A. Now let me get that into some sort of a writing. Okay, position vector A, so we can still call it A as a vector, is OA with this little arrow on the top, origin to A, goes from the origin to A. That's what it is. Now, if we add another position vector, let's say we've got one over here. This one was A, wasn't it? So let's call this one B, of course. This is to point B. This looks like it might be 4, 1. Should we be a bit more interested in 4, 3 over 2? No. So this is 4, 1. Then OB is just going to be 4, 1, of course. But what if you wanted to go from A to B? Now that's a displacement vector which takes you from one point to another. So position vector is kind of like a specific displacement vector, which is just using the origin. So let me explain what a displacement vector is in similar words like that. Right, I hope you can read this. This is quite important, so I'm going to underline these. Maybe I'll put them in a box. Now, how do you actually work out this vector AB? So AB, if we want to go to from A to B, right, A, B. Well, we're going to go from A to the origin. And then we're going to go, so we've gone down here, and then we're going to go from the origin to B. So we've gone AO to OB. Now AO is actually the reverse of OA, isn't it? So this is just actually minus AO. Minus AO. So we can rewrite this as AB equals OB minus OA. And that's like the difference between the two. And that's how to work it out. So this obviously isn't that clear without a nice little example. So let's get a little question ready for us. This is our question. Can you see it? Yep. P. Now, often when you're doing vectors, you get given them in terms of P's and Q's and that kind of stuff. P is 2 minus 4 and Q is minus 3, 1. The question is, find OP, OQ, and then PQ. So let's start with OP. Now this is easy. We're just going to take our coordinate and turn it into a vector. Alright, done. What about OQ? Same thing. Now for the trickier bit, PQ. Well, it's OB minus OA for that one. So it's O, second letter, OQ, minus OP. So minus 5 and 3. So what do we do next then? We've got position and displacement, operations. The last thing that I wanted to talk about was parallel. See, no, there's one more thing. In true Columbo style, just one more thing. Okay, we haven't spoken about the distance between 2 points. So it's displacement, which means a distance. What about the distance between P and Q? That's the magnitude of the vector PQ, essentially. So, because it's a displacement vector, we've got a different way of writing it. That looks like this. Notice what we've done here is, I feel a bit weird stood like this. PQ, magnitude of the vector PQ, we're just going to write it as PQ, like that. No lines, no anything, it's just PQ. But what we're going to do is, same as in the previous video, it's just Pythagoras. So we're going to do x component squared plus y component squared and square root all of that, and then see where it gets us. And it's going to be that. Just going to backtrack a bit. I've just realised that was a minus 4, so it should be plus 5. I mean, it was always plus 5. It's just I got confused with my handwriting. Okay, so let's do this. So we've got root 50. Let's simplify that. Root 50, 5, root 10. Can we simplify it? Did I simplify it? Oh yeah, it's 25 times 2. And then you go do the square root of 25, which is 5, so it's 5 root 2. And that's that answer. Right, so now we're going to move on to the next and final thing, which is parallel vectors. How do you know if something's parallel? Okay, I've written the little title. I often struggle to write parallel. I don't know whether there's 2 R's or 3 L's or 2 L's or... Anyway, so imagine we're looking at our vectors again. So I'll draw 2 more vectors. We'll call them P and Q this time, just to be different. So we've got vector P and we've got vector Q. Now these 2 lines look like they might be parallel, but how can you check if they are parallel? Now you see, the thing is, if you put, these are vectors, you can move them around. If we put them on top of each other, then you can clearly tell if they're parallel. What you'll actually find is that they'd have the same gradient. That's the thing. If you went across a certain amount and up some amount, if they're parallel, then we could just scale P up to get Q. And that's what you have to do. It's a scale factor thing. So this means that these are parallel if you can write P as some scalar multiple of Q, or vice versa. Now here it might look more obvious that you're going to scale P up to get Q, but you can scale Q down to get P. So what does that look like as an example? Also, I'm going to underline this. Let's have an example. Okay, because I'm running out of space, I'm going to go in for a bit more of a spicier question, just to see what we do. So we've got 2 vectors here. We've got P and Q, but what we've actually got is P is minus 3, 2, and Q is 2, y. We don't know what that y is. What we have to find is the value of y, which makes these 2 vectors parallel. So what we're going to do is we're going to do this first. This is what that looks like. Minus 3, 2, which is P, equals T. T is just our scalar. We don't know what it is. We'll find it out. 2y. That's the vector Q. So if we're going to do a scalar multiply of that out, ends up being equal to 2t and ty. So for this to be parallel, we've got minus 3 must equal 2t, because that's the x component, and 2 must equal ty. So we've got 2 simultaneous equations. The first one's quite trivial. Minus 3 equals 2t, so t is minus 3 over 2. Getting a bit small with the handwriting now. And if we use that value and we put it into there, then when we rearrange that by times and by 2, dividing by that, it's minus 4 over 3. Bada bing, bada boom, that's done. So, that is vectors. I think I messed up a bit here by taking up too much room, so I didn't actually get to use too much over here, but that is it. What we've done is we've spoke about, might as well be on camera, we've spoken about how to do vector operations. We do plus and minus quite simply, yeah. Times in, we can only do by a scalar. Yeah, it stopped filming. It stopped filming. Right, so we've got our scalar multiplication, then we've got position and displacement. That's pretty straightforward. How to find the distance between 2 points, and then how to find parallel vectors. What comes next is applying all this to figure out geometrical problems. And that is it.